Insert in linked list. Insertion in a linked list is the process of adding a new node to a linked list. In the previous lectures on linked list, we already discussed that linked list supports dynamic insertion. Let us see how this dynamic insertion works by taking an example. If this is the linked list you are having, we already discussed that there will be something called a head pointer. This head pointer will tell you where is the first node of the linked list. After that, each node will point to the next node that is present in this linked list. That is how each of the node is linked. Let us put some numbers here. Let this be 35, 42, 28 and 3. Let these be the numbers in the linked list. We want to do insertion in this linked list. Depending on the position of insertion, the case of insertion may differ. That is, the way you have to proceed with insertion, the process will differ depending on the position you are inserting. Let us see each case of insertion and what are the time and space complexities in each case. We'll see the procedure and then try to understand time and space complexities. As I told you, whenever you are learning about any algorithm, make sure that right when you see the algorithm, you should be able to understand the time complexity and space complexity. If you are able to understand this, that means you understood the algorithm very clearly, because then only you can have a clear estimate on what is the time complexity and what is the space complexity. Let us start with this. The first one, the easiest case of insertion, it is insertion at the beginning. What if you want to insert at the beginning of your linked list? Here, this linked list is starting with this node which is having value 35. Let us say you want to add a new node with value 21. This is what you want to do. If you want to add at the beginning, what are the steps to be followed? So the first step, whenever you want to do insertion anywhere, the first step is always to create a new node. That is, you have to allot memory. Here it is dynamically inserting. What is dynamic here? You are dynamically allotting memory to a new node and then you are adding this new node to the existing list. That is why you are calling it dynamic insertion. So the first step is to create a new node. You are creating a new node and then you have to put the given data inside the node. Here the data is 21. So inside the new node you have put data 21. What is the next step? We know we have to place this node here. This is the final task. You want 21 to be the first node in your linked list. If you want to do this, presently whatever the head is pointing to, that is your head node. That is the first node. What do you want to do? You want to make 21 as the first node. If 21 is the first node, whatever is presently the first node, this should become the second node. How can you do this? In order to do this, the next pointer of your 21, this should point to whatever is presently the first node. How will you do this? You will check the head pointer. Whatever be the node pointed by the head pointer, you will make 21 point to that node. This is the first step. That is after creation. The second step is to make new node's next pointer, whatever be the new node, its next pointer should be pointing to the present head of the list. So how do you understand head? You have to go to the head pointer and see what is being pointed by the head pointer. That is what we did here. After this, is the work done? The work is not done, because even now, if you just go to this linked list, how do you go to a linked list? Going to a linked list means going to the head node. If you go to the head node right now, it is still pointing to 35, which means as of now, if someone asks you what is the first node of this linked list, you will go to the head and see which is the node pointed by head, which means you are again going to start from 35 and the next nodes are 42, 28, 3, etc. So in order to make sure that 21 is your new first node, what do you have to do? You have to make this head pointer point to 21. So instead of 35, your head pointer should now point to 21. This is the major change. Once you make both these changes, so the next change, the final changes, update your head pointer. Once you update head pointer, 21 is your new first node. What is the time complexity of this operation? If you see for the time complexity, you simply have to check whatever is pointed by the head. Then you have to make new node point to that one, and then head is made to point to the new node. These operations are all constant time operations and it does not depend on whatever be the size of your linked list. Let us say there are a total of n elements in your linked list. This operation that we discussed, it has no relation to whatever be the size of your linked list. You are simply looking into whatever is your first node. Because of that, your time complexity will be order of 1. It is a constant time operation. Why is it constant time? It is because it is not dependent on whatever is the size of your linked list. What about the space complexity? Again, you are not using any additional space other than the new space required for the new node. This is anyway required. Other than that, there is no additional space, and because of that, it is again constant space operation. Why is it constant space even though you are using this additional space for the new node? This is because this new space, this is not dependent on the input size. Whenever you say something like space complexity order of n, order of log n or whatever, that means your space is dependent on the input size. Here, whatever be the input size of your linked list, whatever be the total number of nodes present, that does not influence the space used for this operation. That is why it is order of 1 space complexity. This is it about insertion at the beginning. Let us see the next case. Next case is, what if instead of beginning, you want to do insertion at the end of the list? Let us see this case. I am going to erase this off. Let us say this is still pointing to 35. We still have our old linked list. What do we want to do this time? Let us say the same value 21 has to be added at the end of the linked list. That is, after 3, you want 21 to be added. What is the first step? First step is always the same. You have to create a new node which is having value 21. Creation means you have to allot memory for this particular node. Once you do that, you have this new node 21. The next step, so the first step is again to create. After creation, next step is to put this node in the right place. What is the right place here? Right place is after 3, that is at the end of the list. If you want to add this here, how will you reach this point? Given that this is a linked list, you do not have direct access. What do you have to do? You have to go to the head node. Then you will reach whichever be the first node of your linked list. From there, you have to keep tracking the next pointer of your node and go to the next node. Again, you will see what is the next pointer of this node and you will reach the next node. Like this, you have to keep traversing through your list till the point you reach the last node. Then the question is, how are you going to identify this last node? How will you know that you have reached the last node? Here the point is, whenever the next pointer of your node is a null, that is, there is nothing to point to, that means it is the last node. Because if it is pointing to something, then this cannot be the last node because you have something as the next. Instead, if the next pointer is null, that means this node is your last node. So when you are traversing through the node, keep checking for the next pointer. Whenever your next pointer is null, stop there. Then you will find whichever be the last node of this linked list. What is the next step? If this is the new node with value 21, you have to make the last node of your linked list point to 21. So once you found out whichever is the last node, make it point to 21. How are you going to make it point to 21? Just edit the next pointer of this node. Whichever be the next pointer, make it point to your new node. This is the step. So given that you have already set the next pointer of the last node to point to the new node, your process is done. You don't have to alter head pointer like you did in case of beginning. Here you simply have to update one next pointer and your job is done. What is the time complexity here? In case of your insertion at beginning, we saw time complexity was order of 1. Here, is it still order of 1? It is not. The reason is here, depending on the size of your linked list, that is depending on n, you will take more and more time if the value of n is larger. This is because you have to traverse from one end of the linked list till the last point of the linked list. Because of this, your time complexity will be order of n. Whatever be the size of your linked list, linear to that, you have to use time. What about the space complexity? The only space used is for creation of new node, and as we discussed in the last lecture, for the same reason, space complexity is order of 1. So it has time complexity order of n, but it is a constant space operation. One more thing I have to tell you here is, it need not always be order of n. There is a trick if you want to do this in order of 1 time. How can you do this in order of 1 time? In order to do that, along with this head pointer, you have to do something more. That is, instead of just keeping a head pointer, keep 2 pointers for the linked list. One will be your head pointer, which will point to the first node of the linked list, and keep one more node which will point to the last node of your linked list. You will call this as tail pointer. What is the advantage now? Now, directly you know which is the last node. You have a tail pointer which will directly tell you whichever is the last node of your linked list. So if you are keeping a tail pointer, then your time complexity is order of 1. Why is this? Because you no more have to traverse through the linked list in order to find the last node. This time you have a tail pointer, because of which you can directly access the last node, and in this case time complexity of insertion at end is order of 1. So generally if someone asks you, you will say order of n, because tail pointer is not generally kept in a linked list. But if you are having a linked list in which there is a tail pointer, then your time complexity will be order of 1. Next thing is, we discussed how to insert at the beginning. We also discussed how to insert at the end. Next thing is, how can you insert at a specific position? The third case is specific position. What did I mean by specific position? Instead of beginning or the end, if you want to insert at any particular position, how are you going to insert? See, even insertion at beginning and end can also be put into this case. That is, if you put position as 0, that means you want to insert at the beginning. If you put position as the last node, that means you have to insert at the end. Similarly, whatever be the position you want to insert, let us say you want to insert in some random position. How are you going to do this insertion? For this, again, first step always remains the same. Create a new node which is having value that is to be inserted. Let us say you want to insert 21. I am removing this off the insertion that we did in the last lecture, last case. You want to insert 21. This is the requirement. First step is you created a new node which is having value 21. Next thing is, in case your insertion is to be done at the beginning, then simply call the method that we already discussed for beginning. We already discussed how to do insertion at the beginning. So just call that method, nothing to be done. Otherwise, if you have to insert in any other specific position, follow whatever I am going to tell you. The procedure is, you have to traverse the list to reach the node that is just before the desired position to be inserted. Let us say you want to insert at this position, that is position number 2. Here I am using indexing starting from 0. So position number 0 is this, 1 is this, and 2 is this. I am telling you that I want to insert at position number 2. That is, instead of 28, I should be having 21 there. I am not deleting 28 off. Instead, I am inserting a new element which will take this space. So 28 will be moved to the next spot. That is what is going to happen. What should I do now? Should I go till 28? No. This is the most important point to understand in insertion. Whenever you want to insert at any particular position, do not traverse and reach till that point. Instead, traverse one node before that. Whenever you reach the point where you are one node before the actual position of insertion, stop there. So you have to stop at one node before the actual insertion point. What should you do now? From here, so you are standing here right now. Your insertion point is at 2. You are standing at 1. Standing at 1, what are you going to do? You want to set the new node's next pointer to the next of the current pointer. That is, your current pointer is this. It is pointing to the position before the position of insertion. You will have your new node here. Let us say your 21 here. What is the first thing to be done? You want to make your new node's next pointer, that is this pointer, should point to whatever is the next pointer of your current node. Next pointer of your current node will be pointing to whichever is the position at which you want to insert. So presently it is pointing to 28. What should you do now? The next pointer of your new node, that is next pointer of 21, this should point to 28. That is, it is now pointing to whatever was previously pointed by next pointer of 42. What is the next step? Once you are done with this, then you can update the current node's next pointer to the new node. Current node means wherever I am standing right now. Okay. I am going to update this next pointer, current node's next pointer, to point to the new node. Now you can see that the job is done. The new linked list includes 21 and it took position number 2. And what happened? 28 is moved one position towards the right. Keep one thing in mind. This is very important. The order of operation that I mentioned here, that is of very utmost importance. Why is it? I'll show you with an example. Let us say you didn't follow this order. Instead of doing this, what did you do? You tried to do what I said second in the first place. That is, instead of updating this and then removing this, you decided to first remove this pointer and update it to point to 21. What happens now? The problem is, given that you removed the pointer that is pointing from 42 to 28, that is to the next pointer, now there is no way for you to reach 28 at all. Given that this is a linked list, the only way to reach any particular node is to start from head and keep traversing till that node. What did you do right now? You removed the link from 42, which was pointing to the next node. And what did you do? You made it point to the new node, and new node's next pointer is not pointing to anything, which means you lost the connection to 28 forever. That means 28 and all the nodes which are after that are not reachable now. There is no way for you to reach any of these nodes. Because of that, whenever you want to update pointer, keep in mind that you should always make sure that the linked list is reachable. In order to make sure that it is reachable, if you want to update any next pointer, make sure to point to the next node using some other pointer. What are we doing here? You know you have a new node. New node is directly reachable. What do you do now? Make sure that new node's next pointer will point to this. So even if you remove this, you have some way of reaching 28 now because new node is directly reachable. You newly created it and you can directly reach there. What can you do now? Now you can remove this link from 42 and make it point to 21. So this is how you insert at a specific position. What are the time and space complexities? Coming to the time complexity of this, we always have to see for the worst case time complexity. See, in best case, if your position of insertion is beginning, you can say it can be done in order of one time because you will be calling the function of beginning. But what is the worst case scenario? In worst case scenario, this position can be the end position. It can be the last node. What will you do then? You have to start from beginning and keep traversing till the end of the node. If you have to do that, then your time complexity will be order of n. So time complexity of insertion in a linked list at a specific position is order of n. What about the space complexity? Again, as we discussed in previous cases, we are not using any additional space other than the space that is required to create new node. So this is not dependent on size of the linked list. You are creating space for just a single node. This means space complexity of your operation is order of 1. It is a constant space operation. Insertion at a specific position, it takes time complexity order of n, but it is a constant space operation. In the next lecture, we'll see pseudocode and we'll see how to write it in code on how to do insertion in a linked list. Once that is also done, you'll be very clear on how to do insertion in a linked list.